Hello everyone. My name is Trinayan Barua and I'm here to present our paper GNNMark, Characterizing Graph Neural Network Training on GPUs. This is a paper in collaboration between Northeastern University, Boston University, UCAM, AMD, and KAIST. Here is a brief outline of this talk. We are going to take a look at what this paper is about and how this benchmark suite was designed. Then we are going to take a look at what we use for evaluation of the benchmark suite, some of the characterization results, as well as conclude with some future work. So as you know, most of the real world data today exists in the form of graphs, whether it be a web graph, a graph used for recommendation, or even a molecule. A lot of this data today exists in the form of graphs. So GNNs have been designed as a way or a machine learning algorithm to deal with such graph-based data. So the problem is that conventional DNNs, which are developed for image or text, such as the popular ResNet or AlexNet, cannot deal with graph datasets. And there are a number of reasons for this. The first is that graphs are inherently non-Euclidean, unlike image and text. They also have a very complex topology, and the graphs can be an arbitrary size. So this makes it challenging to define operations such as convolutions on a graph. So what the machine learning community has done is over the past few years, they have come up with graph neural networks, which are an alternative to allow training of neural networks on graph data. And overall, GNNs can be used for many different tasks. So which is not limited to doing things like understanding node importance in the graph, recommendation systems, as well as drug discovery. So here's a chart from the popular machine learning conference ICLR, and this shows the 3-year growth of GNN-based models in machine learning conference. So as you can see, over the past 3 years, there's been a significant increase in the amount of effort that has been put in developing graph neural networks. And this is because the machine learning community has realized the important power of this type of machine learning algorithms because they are able to deal with much more complex graph-based data that conventional DNNs cannot apply to. So overall, there has been an increase in the amount of effort that has been put into this field. Now, coming to take a look at how the graph neural network training occurs. So let's say we have a graph which has different nodes which are labeled as A, B, C, etc. And the properties are the different features. So what happens during graph neural network training is that we are trying to learn how A relates to the rest of the graph. So the process happens through mainly 2 steps, which are called as aggregation and update. So during aggregation step, the node A would collectively pool or collect the different features from the different nodes and do an operation on top of them. So this operation can be what is called as a mean aggregation, max aggregation, or even an LSTM aggregation. Once the aggregation step is done, the node is then updated, which is called the update step. And this update step is much similar to a traditional MLP. So at the high level, again, this training process basically involves aggregation, update, and then these steps are performed over a set number of epochs. And if we look at most of the papers in machine learning, they ideally propose like new aggregation and update functions and how to take advantage of them. Now let us take a look at our suite design. So first of all, why do we even need a new GNN-based benchmark suite? First of all, they represent an emerging class of machine learning workloads, as we have established before, and they are fundamentally different from conventional DNNs. The other challenge is that the existing suites that are present today for our community, such as MLPerf, TBD, FATOM, so these suites do not have support for GNNs currently. So the goal of GNNMark is to be complementary to these suites and provide a diverse suite of GNNs in different domains. And these GNNs will ideally operate on different types of input graphs. We'll take a look at what are the different input graphs that are currently included, and also enable scaling studies on multi-GPU systems. Right now, the goal of GNNMark is to focus on GPU training, but we are also planning to extend it for inference studies as well. Now, taking a look at the application domain that GNNMark covers. So we surveyed a wide variety of machine learning papers and observed that overall GNNs are finding application in some of these major domains. The first is, of course, recommendation systems. They are being widely used in time series prediction for dealing with dynamic graphs. Molecule classification is another area where GNNs are being quite useful. Then when it comes to text, there can be different domains. For example, automated text generation is one field, and then there's, of course, sentiment classification. So we included applications from these different domains as a part of our suite. Now coming to take a look at different GNN types, we of course have the popular GCN, which is the one of the first popular graph neural networks which are published, and many of the future models are actually based on variants of this. So GCN stands for Graph Convolutional Network. Then we have a transformer, which is somewhat borrows ideas of attention from the transformer in DNNs, and then applies them to graph neural networks. We also have LSTM-based graph neural networks, such as the tree LSTM, and GANs are another class of graph neural networks. So similar to GANs in machine learning, which is very useful because they can be learned to train on less amount of data, and they have been found different applications as well. So similarly, GANs are also being explored for GNNs. And finally, we have spatiotemporal GNNs, which are designed to deal exclusively with dynamic graphs, like, for example, traffic graphs that evolve over time, sensor networks that evolve over time, etc. So we try to include different types of these GNNs in GNNMark as well. And finally, there are different types of input graphs, so which I briefly mentioned before. First of all, we have homogeneous graph, where the graph contains nodes and edges of a single type. Right? If you think of a social network graph where you're collecting just people, and whether they're connected to each other or not, that will be a homogeneous graph. Heterogeneous graph would contain nodes and edges of multiple types. For example, a music recommendation graph, where the music and the users represent different nodes, and then you would connect these nodes via edge. And finally, we have dynamic graphs, where the property of the graph itself can change over time. So, for example, in traffic data, when dealing with traffic data, the traffic patterns can evolve over time. And so we need to find a way to process this data along the temporal dimension as well. So based on these principles or criteria, we have curated our suite from open source implementations of different GNNs. So these are the applications that are currently part of our suite, and we are continuously investigating what more applications to add as well. So one of the important things is that we also added multi-GPU support to these models, because we want to study the scalability aspects of these models. So I won't go into details about the models in here, but you can find more details in the paper. Now, taking a look at the evaluation methodology. For evaluation, we use, for single GPU experiments, we use an NVIDIA V100, and for multi-GPU, it's a 4 GPU system on Amazon EC2. All the multi-GPU systems are connected using NVLink 2.0, and we use versions of different library versions of CUDA, CUDN, and PyTorch Geometric, and DGL, which are popular graph neural network libraries. And for multi-GPU implementations, we modify the code to use the distributed data parallel feature provided by PyTorch. So this is basically enables data level parallelism among the different applications. For profiling on the V100, we use NVProf, and we also use NVBit for binary instrumentation to collect the training sparsity information, which is basically understanding how much sparsity is present in data from CPU to GPU during transfers. We leverage a modified version of PyTorch to collect that information. And also we profile for 50 invocations or one epoch of the same kernel, and then average this result across the invocations. Now, taking a look at the results. So first of all, following are the major type of operations that we observe during GNN training. GEM is, of course, present in many of the workloads, and we also have this new kernel type, SPMM. So SPMM is a sparse matrix and dense matrix multiplication. So that that is used in the aggregation step, especially in code from DGL. So the deep graph library, they seem to rely on SPMM for doing the aggregation step, as it's more memory efficient. The other way to do aggregation is through the PyTorch geometric method, which is scatter and gather, and that seems to occupy more memory during training, or it can result in a memory explosion. So SPMM is an alternative which is much more memory efficient. However, there are certain conditions that must apply to be able to use SPMM. And then there's, of course, element-wise operations are also quite dominant in GNN training. And then there are other operations such as reduce, index selection, sorting, etc. So the paper goes into more depth about different applications, like how to break down across different applications. However, here we're just showing two applications, which is PinSage and Arga. And for PinSage, we have two datasets, Movie Lens and Now Playing. And for Arga, we have three datasets, Cora, Sightseer, and PubMed. So the main takeaway from this graph, where the x-axis is showing the breakdown across different applications, and we are also on the y-axis, we are showing across the different applications and datasets. So the main takeaway here is that different applications would spend different chunks of time in different operations. For example, if we take a look at gem itself, right here, we can observe that in pinsage, the amount of time spent in gem is much different than the amount of time spent in gem in Argo. The other interesting thing to notice here is that if we take a look at this reduced portion for Argo, we can observe that even in the same application, depending on the input graph, the amount of time spent in a particular operation will be different. And this creates very much a challenge for developing, say, like a customized accelerator for GNN training, because you have different applications that spend different amount of time in different operations. And even if you design for one application, depending on the input graph, you would have to take into account that they might spend a different amount of time in different operations. Now we also analyze the GFlops and GIOPS and observe that the average GFlops is around 214. The GIOPS rate is 705. So this is much lower than the peak GFlops of 14 teraflops of the V100. And one of the things is that larger batch size is definitely likely to improve this. But based on our survey, we observed that most of the GNN training published in literature seems to rely on smaller batch sizes. So in the future, it will be very important for GNN researchers to come up with techniques to enable training with larger batch sizes, because that's likely to improve this number of GFlops and GIOPS. And because of this reason, GNNs are also another problem is that GNNs are also memory intensive because of the operations such as scatter and gather. So these kind of operations are not computationally efficient. So overall, we observe a very low IPC of 0.55. So that's much lower than what's observed for traditional DNNs. We also did a stall breakdown trying to understand how the application is stalled by different types of stall from NVProf. So overall, we observed that most of the execution stalls is from memory dependency, execution dependency, and instruction fetch. So memory is definitely a bottleneck, as we observe very low L1D cache hit rates. And in general, like the regular operations such as scatter gather, they have higher stalls due to memory dependency. One of the interesting things that we observe is that there's a good percentage of stalls due to instruction fetch. So this is, even though the V100 has a dedicated instruction cache, this still seems to be one of the reasons for dominant stalls. So it should probably look at how to try to improve or reduce these instruction fetch stalls, so that can have a positive impact on performance. We did another studies with multi-GPU training across some of our datasets. So this was on the Amazon EC2 server. So one of the things is that we observed that not all applications scale well with multiple GPUs when using the simple distributed data parallel approach. So this basically splits the data across multiple GPUs and then averages across training epochs. So this leads us to believe that more fine-grained graph partitioning approaches that have been proposed in literature, such as NewGraph or the approaches such as the ROC scalable system, will likely lead to better performance. However, since some of these implementations are not available online, like publicly, we haven't been able to test them and compare them against this distributed data parallel approach of PyTorch. One of the things that is important to note here is that the pinsage version that we have, this does not perform or scale well with multiple GPUs. And the reason we investigated and found it is the sampling mechanism that is used in this implementation. So what happens is that, basically some of the same data gets replicated across multiple devices, and this leads to a lot of redundant computation and even a lot of extra overhead in communication. So this harms performance. We also have other results that are included in the paper as well. For example, low L1D cache hit rates, like 15%. We did observe the L2 cache hit rate to be significantly better, around 70%. However, one of the other things that we observe is that 32.5% of the load instructions are divergent, in the sense that they access more than one cache line. So it's likely something that can also be improved. Then when it comes to training sparsity, which is the sparsity of the data transferred from CPU to GPU, the average is around 43.2, and this can also vary with the input graph. Another interesting observation that we had is that we observe a higher percentage of in32 instructions across many of our workloads when compared to floating point 32. So focusing on the performance of integer instructions is also going to be important. So now, to conclude, in this paper, we propose a benchmark suite GNNMark for GNN training on GPUs. So this is publicly available at this link. I encourage you to check it out and even contribute or work together. The suite is composed currently for each set of workloads, as we explained, on different domains and graph data. Some of the future potential work that we are looking at is, first of all, we want to integrate a time to train metric in the suite. So that would enable a much better comparison with multi-GPU training as opposed to just comparing, for a set number of epochs that we currently did. We also planning to augment the suite with some pre-trained models for inference studies, because the same models can definitely be used for inference. So all we need to do is provide a pre-trained models, and then we can run architectural characterization experiments or even benchmark different systems. And then as the suite continues to grow, we are looking at including more datasets and GNN models. Some of them are the Twitter temporal graph network, which is quite new, as well as reinforcement learning GNNs, which have been investigated in machine learning. So we'd like to thank AMD for supporting this work, and also the anonymous reviewers for their feedback to improve the quality of the paper. Thank you, and if you have any questions, please email me, and also please check out our repository that is available here. Thank you.